All right, everybody, our next concept we're going to talk about is Norton-Thevenin equivalents. And this one's going to take a couple projects to fully explain it, and that's just because of the Multisim Live free account restraints. So I've got this first circuit here, and if we look at it, I've got this circuit, several resistors, a current source, and a voltage source. Now, these switches here are just to show a difference between my functioning circuit and what I'm calling a load, so an unchanging portion. What I'm going to do by using Thevenin and Norton is I'm going to use all the stuff we already know to simplify this into an equivalent, to where I can reduce it down to either a voltage source and a resistance or a current source and a resistance. And if you remember from source transformation, we're going to keep the same property as a voltage source with a series resistance or a current source with a parallel resistance. And I could replace all of this with two components and attach it, and I'll get the exact same properties here. The way we can do this is, say we have a circuit that's driving a load, say it's an 8 ohm speaker or a motor or something like that, and we want to experiment with different loads, but we don't want to risk damaging our overall circuit. If we can find the equivalent circuit, we can then create that with just a power source and a resistance and attach the load to it and get the exact same functioning. And as we change our load, we can see how our power output changes or something like that, whatever it may be. So here, the first thing you have to do to find either Norton or Thevenin, you have to find the equivalent resistance of the circuit. To do that, you have to remove the sources. And just like with our source transformation and our superposition and all that stuff, we short out our voltage sources and we open our current sources. So here you can see it shorted, here you can see it open, disappearing. And from this, we can just use series parallel resistance calculations to find the equivalent resistance from this point to this point. And so we just have a series connection here, so that's now 1,240. Here we have a parallel connection. This comes out to be 90.90, 90, 90, 90, and repeating. So we can just say you can round that best you want, but then when you add these two together, you get an equivalent resistance of 1330.9090, and I just stopped at 9 because that's all my calculator showed me when I did this. So we have to know this equivalent resistance before we can go any further, and this applies to both Norton and Thevenin. So now I'm going to go back and look at my other circuits. So first we're going to go to Thevenin. And if you look here, I have the original circuit, and then I have my original circuit. I have this one just to show you what we have to find without doing all the calculations, because you're going to get bored by the calculations. And then I have my Thevenin equivalent here. So I'm going to go ahead and run these while I do the talking. But to find a Thevenin equivalent, what we have to do is first find our equivalent resistance, but then we have to find the voltage from basically that appears across our load, so from here to here. And you apply all of the other analysis methods that you know of to figure this out. You can use source transformation, you can simplify it by combining series and parallel connections, and I ran through all the math to double check that Multisim was showing me the right thing, and from here to here there is a 335.45 volts with it opened. If we close it, it changes everything drastically. We want an open circuit voltage, and so we get this. And so our Thevenin is this voltage in series with our equivalent resistance. And you can see here that my Thevenin equivalent resistance is providing the exact same voltage across our load, which means there's the exact same amount of current flowing through these. And so now it's kind of unrealistic for you to create a 335.45 DC volt supply in your lab. Some of you may be able to do it, but I don't recommend it. That's a lot of DC voltage and you can do some serious damage. But you can at least simulate much easier. Now you have to think, if you've got a circuit with thousands of components in it, this becomes an extremely powerful tool to know, so you can see how it affects different loads. It makes it easier for your simulation software to calculate this than a circuit with thousands of components, because it has to do that many more calculations. So that's what Thevenin is. It's basically just simplifying a complex circuit down to a series voltage resistance circuit. And then if we go back and look at our Norton equivalent, Norton equivalent is basically the same thing, but instead of finding the open circuit voltage, we're going to find the short circuit current. So here I have the exact same circuit, and all I did was remove my 8 ohm load to short circuit it, and I closed my switches so current would flow so I could see what it is. Now we can still do all the same calculations using all of our various tools to find out what that is mathematically. I'm doing the shortcut just so you can see it, because you don't want to look at a wall of numbers and equations. And then once you find that, you just put it in parallel with our equivalent resistance, and we can see that we provide the exact same current flow to that resistance, which means we have the exact same voltage appearing across it thanks to Ohm's law. And now that's as simple as Norton and Thevenin is. The only hard thing about Thevenin and Norton is determining this current or this voltage. That's the reason we talked about all those other theorems and analysis tools first, because it's kind of difficult to figure that out quickly just by looking at it the way it is. There's not really an equation you just apply to it, it's a whole bunch of equations. So we could, do a source transformation of this into a current source, a parallel resistance, then we have 2 parallel resistors that we could simplify into a single one, and then we could source transformation our current source in a single resistance back into a voltage source and a series resistance, and then we have 2 series we essentially got rid of this. We could then combine those, or we could leave it there at a current source and determine what our 2 current sources, how they divide up amongst all this. That's fairly simple math there. But I went through and did all that on paper just to prove. So if you have any questions, feel free to reach out to me about that, and we can kind of walk you through this, these examples of Norton Thevenin equivalents. But I know this is a really quick, fast explanation of it. I didn't want to bring the math in because all the math is just stuff you should have already learned at this point. The Thevenin and Norton equivalents are a tool to help you really do what-if analysis, or make changes to, or do faster analysis of loads. It is a powerful tool. Where you use it in the real world is going to vary drastically depending on what you're doing. But I hope that helps you, and good luck, and we'll see you next time.